2, 1, so derivative of a derivative. So in calculus, when you're studying, especially in the beginning, students kind of get tripped up on the fact that they're taking these derivatives, which basically yield another function for us, which is just the rate of change at every single point that, say, the rate of change is actually defined at. Now, once you take a derivative of a function, so we certainly can designate it. So, if we went on and tried to take the derivative here, we might designate it like this. Of course, we can also designate it like this. Or if we take the actual function itself, we might designate the derivative this way. Now, when we have this derivative, nothing actually stops us from taking the derivative of the derivative. Because remember that this is nothing else but just a function. So it's some function that we have. And we can certainly take derivatives of functions. So if you take an example right here, so let's say, we'll do a very simple example. So let's say f at x is equal to, let's say, x cubed right here. Now, this function, so we kind of know what it is. It's it's a cubic. So if you know the parent functions, you definitely do know how it looks like. And we can certainly take the derivative of this and we'll say that, okay, well, the derivative of this is nothing else but just 3x squared. So the cubic now becomes basically just a parabola, right? So there is, a scaling of 3, but it's nothing else but a parabola. And this just tells us what the rate of change is at every single point of this function, right? And that's great. And now if someone would say, well, what if I gave you this function to start with? Could you take the derivative of that? And the answer is, of course, I could take the derivative of that. That's not a big deal. In fact, I can go ahead and take the derivative, and this would be just simply 6x. So it would just be now a straight line with a slope of 6. And this would have been my second derivative. So this is the derivative of the derivative. And we actually have a designation for this. So in terms of writing this out, it may or may not surprise you. Okay, so with respect to the original, we kind of put these two double primes. This would just mean that this is the second derivative of the original function that we had, which was f right here. So that's what we were dealing with. Now, this second derivative that we have doesn't mean that we have to stop there. We can just keep taking the derivative over and over again. Now, eventually, in this particular function, eventually, we're going to run out. So this would have been a second derivative. If I wanted to take the third derivative, so if I wanted to take now the third derivative, then this just simply means 6. Now it's a constant, right? So here the third derivative is a 6. And now if I wanted to take the fourth derivative, and by the way, for having derivatives, sure, we put a prime, and second derivative, we put a double prime. But once we get to kind of 3, and then 4 and so on, we don't really want to be writing all of these primes. So technically, we start writing it with actual numbers. So this just means the fourth derivative of our function, and in this case it would have been 0 because this is a constant. So we have this chain of derivatives. So we started off with one particular function, which was x cubed. We took its derivative, so here's the rate of change of that function. And then, we could have taken a second derivative, so here it is. Here's the third derivative, and then here's the fourth derivative. And, the fifth derivative and onwards, well, it's always going to be now 0 because this is just flat. Now, in general, actually, I wanted you to know that if you are taking derivatives as you're going on, instead of writing the little primes, we do technically, if you want the nth derivative that you want to be able to take, then we simply designate it with an whatever function it might be. So this would be f, and then we would simply put an n in here and x. Now, this is much different, and I certainly make this mistake at times, but if you want, to designate and make it different, from this, which means you're taking the function inside of here and you're multiplying it by itself n times, so really it's just an exponent. So that's the designation and difference between an exponent designation and a derivative designation. So please, if you are going to be doing exponents, try your best not to write it in this particular way, because some people will be thinking, well, is that person talking about the derivative or is it an exponent? So to make it explicit, I always say just put it in brackets, the function itself, and then put the exponent on top so that it's very clear. Now, for the most common derivatives, which is the first derivative to get the rate of change, and then the second derivative, which is just the double prime that we use, then there's really no problem. You don't have to write, two meaning for the second derivative. You will just see the double primes, okay, beside it. So it won't really do any confusion. And those are the most common ones that we see. Now, I do want to, take this a little bit further with you and kind of give you an example. So this one was a very simple example, but I want to also make you visualize, what is happening here with regards to taking these derivatives, to think about, the rate of change. Because once you start applying derivatives, you're going to get into certain applications where some intuition into what you're doing is kind of useful. Now, when we're just talking about some random x, we don't know what this quantity is, then it's very hard to make it intuitive, aside from the fact where you can just kind of draw it out, right? And then see for yourself what's happening. But when you tie it into an actual application, maybe, you start talking about distances and speeds or velocities and accelerations. So things that are, kind of taking on a certain speed and possibly speeding up or slowing down, then there's going to be meaning to those. And of course, there can be other applications. So with these first and second derivatives, before I end this video, I want to give you, let's say this example. It's still not a very hard one, right? If you've watched any of my videos, then, we have taken derivatives of much harder things than this in the beginning, especially, if I did a summary of all the different derivative rules, for example, I really tortured you with an example there. Okay, now if you want to watch any of that, I'll put up a link up above there for you if you want to remind yourself of the derivatives. But here, for this example, if this was our original function, what I want to be able to do is to walk you through kind of what's happening and how you can think about intuitively about these derivatives, especially the first and then the second one. The first one you more or less know because it's rate of change. But then going from the second to the third, okay, what is actually going to be happening there. So let me plot this out, all right? So I'm going to plot this out to kind of see how this function looks like. Now, we can certainly plot it on our own and sketching, and you get to a chapter in calculus, for instance, where you're going to do some sketching utilizing the derivatives to help you. So you'll get there eventually, but for the moment, I'm going to pull up Desmos in here and try to plot this out. So this is fx, so I guess 1 over 5x, this is cubed, plus 2x squared minus x, and then plus 5. Okay, so let's kind of zoom in here a little bit just so that we can see what's happening there. So there you have it. And now we can put any point we like on this particular graph. So let's define some a. So this would be my value of x. Okay, let's start it off at 0 in here. All right, and then maybe, we'll swing it back in between, say maybe minus 20. Right here, and let's say 20 right there. All right, so here's my point. So that's a. I'm going to substitute that. So I'm just putting in an ordered pair in here, and then I'm putting it into the function itself. So that would have been a right there. All right, so there you have it. And now we can swing this point, okay, kind of moving it around wherever it is that we like. Okay, so we have that. Now, those are the points. Now, if we want the derivative, all right, so let me kind of go back in here. So the first derivative in here, if I go back and try to do this, so my first derivative is going to be equal to, now let's take a look. It will be, so negative 3 over 5 x squared plus 4x minus 1. That is my first derivative, all right? And now this, of course, is a function. So this just tells us what the rate of change at every single point is. And, you know, we can certainly plot this function, right? So I'm going to plot the function in here. So I'll call it, you know, let's say g at x, all right? Or maybe what I'll do is I'll call this f1, okay, kind of for our first derivative in here. So negative 3 over 5, you know, x squared plus 4x minus 1, okay? So that is a function, and, you know, we can see and plot the function in here. So what I want to be able to show you here is, now, this function basically tells us what the actual rate of change is at every single point. So the red represents our original function, and then this represents our actual slope at every single point. Okay, so now with regards to that, so I'm going to put that, let's say, you know, here's my slope. Okay, so slope is equal to just f at 1. All right, so that would have been the slope at whatever point that might be. And now, just to make it very visual, I'm going to put a tangent, okay, at every single point. So now finding the tangent, now I have a point, I have the slope, so I can certainly find the y-intercept for my line that goes through that particular point. And that intercept, so I'm going to call it b, you know, kind of going back to the y is equal to mx plus b. So b is equal to y. Well, y is nothing else but f a. And then the mx, okay, which I can bring on the opposite side as I'm solving. So I'm just rearranging y is equal to mx plus b, rearranging it for b. So this will be just m and then times a. And so here's my b. So now this, so y is equal to mx plus b. Let's see if I did it correctly. So I did. So there you go. So we have right now, I'm going to switch this a little bit out in here. So I have this point, okay, and now I can kind of see what the tangent is, right? Now, what I want you to notice, so as I'm doing this, okay, let me kind of go back in here and squeeze this out. Let's see how far I can push this. All right, so let's say if I have that. So notice that the slope clearly is negative, right? And notice the purple line, which represents my actual derivative, right? So if I'm plotting it up, so it looks like, you know, so here, you know, the slope gets steeper and steeper. And as I come down right here, notice that the slope slowly, okay, loses its steepness, right? So it's less steep here than it was, you know, if I go all the way here. So here it's just getting steeper, steeper, steeper. And now it's getting less steeper. But it's still all negative. And notice on the purple line, what I have is that purple line, okay, is indeed just kind of shifting over, right? So it is there. Now, let me plot in. I'm going to see if I can plot a, okay, in of that. Okay, so there you go. So, you know, so notice that now it's going to be moving along. So this just tells us what the slope is. And if you look on the left-hand side where I defined m, it tells us. So it's negative 140.97. And then now it's going to be less steep, right? So it's coming down in here and it's less steep. And notice that it's moving along on the purple line, just telling you what that value is, right? So now it's becoming less steep, less steep, less steep, less steep, less steep, right? So it is coming closer and closer and closer to basically here, notice, bam, it's going to be 0 somewhere over here. So within here, okay, notice that it changed from negative and now it goes to positive. So within here, if I zoom in, right, so if I zoom in here, okay, you'll notice right there. Now, okay, so it went from 0 right here. So that's the purple now touched 0. Now notice that it goes further. Now it gets positive. So now it's positive until, right, this particular point where now it's 0 again. So notice that it's, you know, that purple line as it's moving along. Okay, now it hits 0. And now the slope starts to be negative again. And that's exactly what we are drawing out right there. So this is an amazing way to be able to visualize these. And now, since we're talking about the derivatives of derivatives, this is all great to visualize for oneself, to be able to see and then understand that the derivative is just another function. Now, if we took another derivative, then really what we would have been doing is we would have been just removing this entirely and now taking this new function, and then someone says, take the derivative of this. Well, and you would say, well, I can do that. That's not bad. I can certainly take the derivative of that. So if I go back to our original here, okay, and now I take the second derivative, so I can certainly try to manage that. So here is my second derivative that I have. So that's of this. So now notice, now what it's going to be, so it's going to be negative. It's going to be 6 over 5x plus 4. And now this, as you can see, is just a line. It's just a line, right? It has a negative slope, negative 6 over 5. The y-intercept is 4. So it would have been just a line straight across that we would have on our plot. So if I go back to decimals, now I'm going to kind of bring back my original here, right? So I have now my red is the official, okay? I actually put it in blue there, so maybe, you know what, hold on, let me see if I can change. Here's the color, so if I just highlight it, so make that blue. Our second one, I made this one green. I'm going to put this one as green. That's going to be our slope. And then here's going to be my third one. So this is going to be my second derivative. All right, so I'll call it f2x. And then equals 2, so negative 6 all over 5x plus 4, which is just a line. I'm going to try to see if I can squeeze that out and make it, oh, I can make it red. So there you go. So that's what I have right there. And then maybe, you know, that y, that original one, will pull it black. Okay, so there you go. So now what we have, if I'm going to squeeze this out, now I have 3 plots. I mean, it's really kind of complicated within here. So I have my original one, right? This just represents what the slopes are. But now I can actually move this, and instead of concentrating on this, I'm going to remove that. And now we can see that if we take the derivative of this one, right, and we would actually put the actual slope. So instead of having the slope right here to be, okay, I'm going to just change this to 2 right there. So that's what that is going to be. All right, so this is that. And then over here, so this is of the derivative, so f1. So notice that's going to be, I'm going to not label that. Now I have this point, and what I'm doing here is I am looking at what the slope is with respect to this line, right? And notice here, okay, so hopefully you can see this. So if let me kind of zoom out here a bit. Okay, and I do this. So if I do this, the green that you see is my first derivative, right? So that's the parabola. It's facing downwards, right? And now if I take the derivative of this, which means it's the second derivative of the original function, and now what I'm really doing is I'm trying to find what the rate of change is with respect to this parabola, right? So notice, so here, the slope is positive, right? And it's pretty steep. And that's exactly, so the red line represents my second derivative. And notice that it is positive at those points. So that's what you see there. Let me go back in here and maybe I'll just plot in that point. So that's going to be on A of the F2. All right, just so that you can see, so that's moving along. Notice it's positive, but now it's getting less and less positive, right? And that makes sense because the slope on this function, okay, is now becoming less and less steep. Now eventually, okay, right here, so it's still positive if I zoom in here so that you can see. So it's still positive, right? But notice that now it's going to be 0. And that's exactly what you see here on the function which represents the second derivative. So it's 0, and now it switches, and here now it's becoming negative, and it's just negative, 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 and more negative. And it's just represented by a line. So that's pretty amazing that we can do that. And you can visualize it with decimals in a pretty neat way. And I would encourage you to try to walk through this and understand, okay, what I have been doing to try to do this. So the whole idea is to be comfortable with just taking any derivative, the first derivative, the second derivative, the third derivative. You know, there will be meanings to it, you know, so as you know, you're going to get into, as I mentioned, distance, for example, speed and acceleration, you know, so the second derivative, for example, will mean the acceleration. It's, you know, how are these things speeding up or slowing down? And that is definitely something that we can think about. Okay, so here, you know, I could have continued this, right, in terms of the third derivative, if I wanted to. So if I went on, so let's say if I continued and I made this the third derivative now, of course, all I would get is negative 6 over 5. And that shouldn't surprise us, because if you look at decimals, right, and you look at the second derivative, it's a line. And if it's a line, then the slope at any point is just the slope, right? So it is just the slope, which is the negative 6 over 5. And if I try to take the fourth derivative, now I'm going to just put 4 in here, then this would have been just 0, because this is just a constant. It would have been flat at negative 6 over 5. So if you take the derivative of that, of a constant, we know that it's 0. There is no slope. And then we're done. There is no further derivatives that we can work with. So you can walk yourself doing derivatives as much as you like. I hope that this visualization has also helped you to think about, like, really what we're doing is we're trying to find this rate of change, which is just the slope on any line. And don't be afraid if someone says, you know, what's the second derivative or what's the third derivative and so on. So, you know, don't get caught up with the notation of it all, as I do at times. You know, I think this is the, you know, the common mistake that I make. Yeah, so I always have to be careful, especially once you start dropping the x, right? Because if you drop the x and you start designating it like this, then, you know, definitely you'd be like, is this a derivative, the nth derivative, or is this just an exponent? So is this just the power of that function? You know, so that's why, you know, sometimes it's worthwhile to keep the x to make it very obvious for the reader. Anyways, I hope that you found this video useful. It's an introduction to, you know, taking derivatives of other derivatives, which basically will now lead to some applications. Okay, we'll see you in a future video. Happy studying for calculus. Bye, everybody.